Donc, on peut commencer?
ان شاء الله ها ان شاء الله غادي نبارطاجي ليكرون ياك بارطاجي ليكرون ça marche.
Voilà, c'est bon. Très bien. Maintenant, j'ai le... Voilà.
صور ما نضربهاش.
D'accord, c'est bon. On va partager, d'accord? Donc, qui va parler, c'est le Moutaoukil, c'est ça?
يا نعم. Yes.
C'est Karim
Moutaoukil, نعم.
Donc, c'est Karim Moutaoukil, c'est ça?
نعم.
Ok, d'accord.
Donc, c'est bon. Je commence?
Ça y est, on peut commencer?
نعم.
Ok, yalla, bismillah.
First, allow me to thank the organizing committee that allowed me to present our work entitled a new recurrent neural network fuzzy network clustering method. This work was prepared by in collaboration between two universities, Sidi Mohammed ibn Abdullah and Virginia University of Brussels, by Karim Moutaoukil and Saadullah Touhafi. The outline of our work is given by first we give some introduction, then we talk about fuzzy k-means. In the third point, we give the principal idea behind the recurrent neural network, especially continuous hopper network. Then we propose. We give our proposal method, namely fuzzy recurrent neural network. Then we test our method on some well-known data sets. Finally, we give some conclusion and perspective. As you know, clustering method can be divided into six categories. Connectivity model, as example, hierarchical method that suffer from similarity choice of similarity measure and stop criterion. Then we centroid models as example k-means and fuzzy k-means that suffer from the initialization problem and local bad local minima. Then distribution model, for example, multivariate normal distribution that suffer from overfitting. Density-based clustering, as example, the BSCAN method that has several parameters which are hard to select and to simulate. Space model, for example, there is the Merkin technique that require large computational effort. Graph-based model that, for example, the one based on max-weak problem. As you know, it is NP difficult combinatorial problem for which we must call other method, optimization method. Finally, neural models, as example, self-organizing map that suffer from the choice of the number of the size of the map. In this work, we propose a new neurofuzzy model based on fuzzy k-means and neural network model. As you know, neurofuzzy system merge both the theory of neural networks and fuzzy set. In one hand, neural network method allows neurofuzzy system to acquire additional information from data. In the other hand, fuzzy system simulates reasoning, human reasoning, especially for clustering issue. Our approach is called recurrent neural network fuzzy mean square for clustering issue. Process and 4 steps. In the first step, we model the mean square, the fuzzy mean square error in terms of minimization of optimization model subject some constraint. Then we construct an adequate energy function that make a compromise between objective function and the constraint. Then we construct an original continuous rapid network or recurrent neural network based on the proposed energy function. Then we call the Euler-Cauchy method to calculate centers and the membership function or the membership degrees. As you know, fuzzy Camis was proposed by Dan, and it is a version of Camis, deterministic Camis. This method is will use it, widely used for pattern recognition. The fuzzy mean square error can be modeled as follow: minimization of some function subject family of allocation constraints, fuzzy allocation constraints, actually, such as the I are the samples, CG are the centers, mu E, G are the membership degrees, G is the fuzzy error square. The degrees, the membership in degrees must sum to 1 to choose only one cluster by degrees. Several approaches can be used to solve this kind of problem. For example, primal approach, I give as example generalized diffuse gradient as example. Heuristic approach like Hell-Landin, simulated analyne, genetic algorithm, and so on. Finality approaches, for example, Danzig algorithm, Ozawa algorithm, and the recurrent neural network. Due its performance and the fastness, we will use this method to solve this model. So we give the philosophy of the continuous rapid network, which is interconnected neural network with smooth sigmoid activation function. The differential question that governs the dynamic of continuous rapid network is given by, such as U is the vector of the neuron states, V contain the neuron's activation function vector, W connection weight matrix, I external noise vector. Finally, tau is the activation function slope. Continuous rapid network can solve any optimization problem from which we can extract an energy function or an energy function. Yes, energy function. In our case, our problem is the proposed model is given in the right. We propose the following energy function, such as GI represent the family of constraints which that is introduced in energy function in square and linear term. Alpha, beta, and gamma are the Lagrange multiplier. Based on the first derivative, we calculate the vector noises. Based on the second derivative, we give the connection weight. The algorithm, the Euler-Cauchy algorithm adopted to our to continuous rapid network is given by first part In the first part, we give some parameter epsilon1, epsilon2 that will serve as step criterion. In the initialization phase, there are two S's which represent the step of other question method. CG0, C0, C0G is the center width. IG0 are the member degrees, which are randomly chosen. To update these parameters, we give this question. First question, in the first question, permit to update the Euler-Cauchy steps. The second question permit to update the centers of groups. This question permit to calculate a first calculation of membership in degrees. Then we project this row, these rows. We can to ensure the feasibility of the membership in degrees. We project the row on the space defined by the constraint. And the last step consists on stop criterion. In this context, we will stop this procedure when the center and the membership degrees don't change anymore. Q is the quadratic term of Taylor exponential of the energy function E in the points U, mu, K, and Ck. The projection is based on the matrix of constraint, which contain only 0 and 1. Our method is tested on two well-known data sets, namely IRIS data that contain 150 samples, and diabetes PIMA data diabetes data set. The characteristic of the machine in which we are our algorithm are coded is given by the parameter or the multiplier of Lagrange are stated as follow in this number. Concerning the test of our method on IRIS data, the table on the left show that our method has the best accuracy in comparison with the classical method. In the right, the figure in the right show that our method don't require a lot of several iterations to converge to best local minima. Concerning the test of our method on PIMA diabetes dataset, the table on the left shows that our method is superior in accuracy term to the other methods. The figure on the right show that our method don't require several steps to estimate the centers and the membership degrees. In this work, we have proposed a new recurrent neural network called network fuzzy mean square cluster method. First, to this end, we modeled first the fuzzy clustering mean square in terms of optimization problem. Then we formulate inadequate energy function from which we extract the weight and the noises of our neural network. Then we call the Euler-Cauchy method to estimate the membership degrees and the center. The proposed approach, as I said before, was benchmarked on IRIS data and the PIMA diabetes dataset. compared to various methods in the literature, our method has the best accuracy. To ameliorate or to improve the performance of our method, one can use genetic algorithm to set optimally the parameter alpha, beta, and gamma. Finally, as perspective, do its performance, we will use recurrent neural network, fuzzy recurrent neural network to cover the need of set of objects in smart city. Thank you very much for watching, and thank you for question. Assalamu alaikum. Please, if you have question, please. Please, if you have question. Assalamu alaikum. Assalamu alaikum. Sukaina, if you are there, please, if you have some question. Sukaina, please, if you have question. You hear me? Anybody there? Please. If someone have question, please. Dear Judy, if you have some question, please.
Assalamu alaikum. Do you hear me?
Yeah, I'm hearing you.
I have a question concerning your data set. You said that you use the Earth data set and the Diabet data set.
Yeah.
Does your algorithm can work on categorical data set or only on numerical data sets?
You know, using dummies, there is no difference between numerical and categorical data set, because we can use technical dummies technical to transform the numerical value to the categorical value to numerical value.
I don't mean I don't mean categorical. Sorry, I mean maybe a data set that contain names of persons. Can we convert these names to numerical data?
Names. Oh, but names, I think that will not have an important effect on the decision process. You know.
Yeah.
For example, if there is no yes, we can.
I understand you. Yes. I have my problematic. I have a data set that contain persons. The attributes are names, last names, and addresses. And I want to cluster this data into clusters so I can detect the duplicate values easily. Is it possible to use the fuzzy k-means?
Yeah. Addresses, we can characterize addresses. For example, for example, the city and the surface and the several characteristics to transform them to numerical value. But fuzzy logic, it's model the reasoning, the human reasoning. If you think deeply, you can use a fuzzy clustering method. But if you want my address, we can talk about this after, inshallah. We can help each other if you want.
Okay. Thank you.
You are welcome. Thank you very much for this question. Thank you. Thank you, sir. Thank you, sir. If there is a question, please. Please, if there is question, please. There, Judy. So the second presentation. So
please.
Okay.
I want to ask.
You're welcome.
Did you make any pre-processing in the dataset before using this model?
I don't understand. If you can explain in the advantage your question, please.
I said that did you make any pre-processing in the dataset before using those models?
Yeah. There are some pre-processing. This is a good question, like the first one, actually. Pre-processing phase. It's interesting, and anyone wants to work in any data must to do it to make compromise between the vector the samples. Yeah, normalization and so and we have centered the data. There are the first pre-processing, and if there is some missing data, we complete it using some well-known method, for example, KNN or another method. It is a good question. Pre-processing. There is another processing. Is the post-processing. There exists another process. It's post-processing. Post-processing. We use the reject group to ensure the security of our system. But it is another question. Thank you for your question there. It is very important. Thank you. Thank you, sir. Please, Alf, I can leave. Please, question, please. Before leaving, I will give my email if someone has question or anything more. I will be ready to change some information that I know it all. Thank you very much. Thank you very much.
Any questions? If you have questions, you can ask. I think we don't have questions, so we can pass to the second presentation. It's learning analysis based. It's about, okay. It's Salim Lahmiri. You can present, please. Salim Lahmiri. You hear me? You can present now? Any of the author can present. I think Salim is not here, so let's pass to the third presentation. Hamid Nasser, can you check please your presentation and start presenting, please?
Yes, can you hear me?
Yes, we hear you. You can start, please.
Do you have the video that I shared with you days ago?
We will check. But if
There-
you can present, it will be better.
Yeah, I can, of course.
Okay.
Okay, I will share my screen.
Okay.
Can you see my screen?
Yes, you can start.
Okay, Bismillah. Hello everyone, my name is Hamid Nasser bin Khalid, and in the next 15 minutes I will present to you our contribution in the field of data quality entitled Block Sizes Control for an Efficient Record Linkage. During this presentation, we will see an introduction, then we will define the record linkage process. After that, we will present our contribution, followed by our experiments and the results. Finally, we will conclude with the conclusion and some future works. We start here with an introduction. As we know, in the recent year, the world is witnessing a huge explosion in the volume of data, specifically after the adoption of smartphones and social media that generates a huge amount of data in a daily manner. Consequently, data integration is becoming an important process for most organizations around the world. Most of them need to integrate their data coming from different sources in different formats. This integrated data is used by enterprises in order to extract useful information out of it, in order to take decisive decisions, such as advertisement investment, and conduct their business in the right way. However, data quality can cause some serious problem. For example, in this slide, we have here some statistics about the cost of data quality on typical enterprises. Organizations lose trillions of dollars per year in the US alone due to poor data quality problems. Many data warehouse projects have been interrupted because of data quality problems. 15 to 20% of the stored data in most organizations is erroneous or unusable. Making decisions based on bad data can end up badly for an enterprise. Data quality problems can appear in different ways and aspects. Generally, the main data quality problems that have to be dealt with are missing values, duplicate values detections, referential integrity issues, and many other issues. Our contribution is in the domain of duplicate value detections, which is also known as the record linkage process. Record linkage is defined as the process of identifying the tuples that refers to the same real-world entity and merge them into a single one. When the record linkage is executed over a single database, it can be referred to as the duplication process. The mathematical formula definition of the record linkage is shown in equation 1, in which we have our relation R and our two tuples Ti and Tg. After applying the record linkage on the relation R, become R minus Ti minus Tg, which means that we remove both tuples Ti and Tg, and we create a new one, which is merging of the two tuples. As we see from the depicted picture, the goal of record linkage is to identify that the first tuple from database 1 represent the same entity represented by the first tuple in the second database, and same as for the second tuple, which means that after the integration of database 1 and database 2, we will have only 2 records instead of 4. The main steps of record linkage. The first step is data standardizing. Data standardization is the process of standardizing the dataset attribute that may represent the same information, but with different identification in each one. For example, we can find that the sex attribute is represented in one dataset as a binary value, 0 and 1, and in another one, we can find it as F for a female and M for a male. So using a unique representation for an attribute is very important for successful record linkage process. The second step is blocking, considered as the most important step during the RL process. Blocking consists of dividing the data into a set of blocks. In that way, only the records of the same block are compared to each other. The last step is matching, in which we can use some string similarity metrics, for example, the aided distance or the Jacquard similarity, or we can use a machine learning algorithm to classify the record as a match or non-match. Blocking consists of dividing the data into a number of blocks. Each block will contain only the record that may refer to the same real-world entity, which means that the record shares a similar blocking key value. For example, all the persons with the same first name will be clustered into the same cluster. A blocking key can be chosen as a single attribute. For example, we can use the first name. Otherwise, a blocking key can also be chosen with the concatenation of several attributes. We can use the first 3 characters from the first name and the first 3 characters from the address. Our main problematic, even when using one of the existing blocking techniques in the literature, real-time RI can sometimes fail to return the query result in the desired time. In fact, the existing blocking techniques can sometimes generate very large blocks, which leads to a high computational time. On the other hand, generating very small blocks can reduce the effectiveness of the RL process. Here we have an example of an Arabic dataset with Arabic names. Using the standard blocking with the first name as a blocking key, created the following blocks. The first block contained 18 instances, while the last one with only 3 instances. This huge difference between the size of the blocks is not good for the record linkage process. As a result, our contribution in this paper, we propose a mechanism to control the generated block size with the k-modes-based record linkage in order to make it suitable for real-time problems. The general idea behind our proposition is as follows. First, we generate the blocks using the k-mode-based record linkage normally. Then we merge all the generated blocks that are under predefined minimum size, and the similarity between their modes is maximized. Finally, we divide the blocks that are larger than a predefined maximum size using another blocking key with the standard blocking. As we said, the first step in our approach is splitting blocks. We start by splitting all the blocks that have a bigger size bigger than max size using the standard blocking with the new blocking key. Of course, max size is a threshold fixed by the user. If the size of the generated blocks is still bigger than max size, then it gets split again with another blocking key until it creates a set of blocks that respect the maximum size threshold. If the size of the generated blocks is under mean size, then it gets inserted to the set that will be treated in the next step, which is merging blocks. To start merging blocks, first we have to sort all the tuples that have a size under max size and crazily according to their size. Then for each block with the size under minimum threshold, we find the blocks that have the most similar mode. If the union of these blocks is still under mean size, then the new merged blocks get inserted into the first list as a new block. If the union of these blocks is above mean size, then the new created block gets inserted into the correct size set. All in all, our overall algorithm, as we said, contains 3 main steps. First, we generate the block using the k-mode-based record linkage. Then we merge the generated blocks that are under a predefined minimum size. Then we divide the blocks that are larger than a predefined maximum size. We pass now to our experiments and the results. To evaluate our proposition, we used 4 real-world data sets. Those were selected because they were used to evaluate several RLA approaches in the literature. The first one is the restaurant dataset, which contains information about restaurants in USA. The second one is the DBLP-ACM dataset, in which bibliographic citations were collected from two different sources. The third one is an Arabic dataset that contains information concerning students from our faculty. The last one is the Cora dataset, which contains publication in the machine learning era with duplicated record. Table 1 shows the detail about the used dataset. For evaluation measures, we use 3 metrics that are used to evaluate any record linkage approach: record linkage, reduction ratio, pair completeness, and F measure. All our experiments were done on a machine with Intel E5 CPU and 16 GB of RAM, and our implementation was done using Java. Firstly, for the restaurant dataset, we varied the value of max size and mean size from 15, 100, and 200, and we measured RRPC and F measure in all these cases. From the obtained results, we can see that choosing the value of max size parameter has a direct influence on the reduction ratio. With small max size values, we obtain a high performance concerning RL, since the data get divided into more small blocks, which mean a less number of comparison between the records. The best RR results was obtained with mean size equal to 50 and max size equal to 150, where RR reached 0.94. The value of RR keeps reducing with the augmentation of max size. In the second experiment, and in order to analyze the changes in the number of blocks before and after block size controlling, we noted the number of the generated blocks after each execution. The obtained results are shown in the depicted figure. As we can see, when mean size and max size parameters were fixed to 15 and 150 respectively, the number of blocks gets augmented. After that, the number of clusters keeps dropping down with augmentation of mean size and max size. The first augmentation in the number of blocks was caused by the splitting of small blocks that were over max size, which was fixed only to 150. On the other hand, the later reduction in the number of clusters is explained by merging blocks that have a size under mean size. In our third experiment, we compared other blocking techniques that exist in the literature. Our proposed K-mode-based ARR with block size control achieved good results based on the experiments that were done on the Cora datasets in Figure 3. We can see that the proposed technique overcomes most of the existing blocking approach in the literature regarding pair completeness, specifically compared to the work of Fisher and al., since we used the same blocking keys and size parameters that were used in their experiments. In the final experiment, we used the Arabic dataset to test the scalability of the proposed block size controlling approach. 3 different datasets were generated by replicating the original data record 5 times, 10 times, and 15 times. We observed the execution time for both cases. K-mode-based ARR without block size controlling and with block size controlling. The results are shown in Figure 3. As can be seen, K-mode-based ARR with block size control has a better performance concerning the execution time than K-mode-based ARR without block size controlling. The gained time was during the matching phase, since matching was done over blocks with controlled size, which means fewer comparisons number. In this, we pass now to the conclusion. In this presentation, we introduced a novel mechanism to control the size of the generated blocks by K-mode-based ARR. The proposed solution was to divide the blocks that have a size larger than predefined value and merge all the blocks that have a size less than a predefined minimum size. And the similarity between their nodes is maximized. The obtained results from experiments on 3 real-world data sets show the efficiency of the proposed approach in detect and duplicate record while respecting the size restrictions. As future works, we aim to propose a solution for controlling the block size of other blocking techniques so they can be suitable for application like real-time ARR or privacy preserving ARR. Thank you for your attention and welcome to your question.
Thank you for your presentation. Sorry, I have just been switched to this session. I didn't attend the beginning of your presentation. I give the floor to the audience for any question. Is there someone who have a question? On my side, you talk about a real-time system, and you have done some blocking to resolve this problem of real-time.
Yes.
What are the real-time constraints you are facing?
We have to detect the duplicate values that we have in our dataset in a specified time, so we don't have much time to return the query results. It have to be
because
done
I didn't see in your paper that you have, for example, in your real-time system, for example, the system should respond before 1 second, 2 seconds, or 1 millisecond, and you tell us after that your system is responding at
yeah, and I understand your question. The problem that the request time, it depends on the size of the data set. If we have a very large data set, the response time depends on the size of the data set. We can't assure that it can be done in 1 second or 2 seconds. If we have a very large data set, for example, in the case of big data sets, our goal is to minimize as much as possible the response time.
Yeah, but not real time, because
yeah,
is other things here.
Yeah, I
understand. Just minimizing the processing time
as much as is possible.
Yeah,
yes.
yeah, I know. Yeah. So, and this blocking doesn't raise other problems. For example, if you divide some strings or other data, random data, there will be no impact on the process and the post-processing after?
The blocking consists of, for example, we have a data set that contains three attributes. Blocking will divide this data. So instead of comparing each tuple to all the others, we will compare only the tuples in the same block. That's
only the variables, not data, not the contents. For example, if in Arabic, for example, we have phrases, and I will divide the phrases in sub-elements. No, it's not this case. But I didn't attend your presentation from the beginning.
No. Blocking consists of dividing the data set by using the attribute. For example, all the records that have the same first name will get assigned to the same cluster.
Okay, thank you. If there's no other question, I will switch to the next presentation. Is there any question? I think there's no other questions, so we will switch to the presentation on artificial neural networks based ensemble system to forecast Bitcoin daily trading volume by Salim Lahmiri, Rafat G. Saab, Daniel Morin, and Fasin Nebebe. You have the floor. Could you share your presentation? Is there someone from this presentation in the audience? I will switch to the next presentation. ID 18 distributed large graph coloring algorithm on giraffe by Brian Hashim Slimani.
Yes, I'm here.
Oh,
Hello.
The ID 18 or
yes.
ID 12? Okay.
18.
So you have the floor.
Yeah, I prefer using the recorded video. I'm not sure about my connection, if it can handle it or not.
Yeah, I will tell the
yes, please.
organizers to schedule the video.
Yes, please. Okay, they said they don't have the video, but I sent it by Google Drive before.
Whoa,
so I try to present, to share my presentation.
We'll see, yeah. Could you share your presentation, please? Well, sorry for this.
No problem. I will try. Yeah, hopefully nothing will disconnect me.
I hope
okay, hope that
yeah. There will be no problem.
Inshallah. So How do you see? Can you see my screen?
There's no problem. We see your screen.
Yeah.
We
Yes. Okay. Hello, everybody. First of all, let me introduce myself briefly. My name is Asia Bregan. I'm a researcher member in the Limad Lab at the University of Bijaya, Algeria. Today, I'm going to be talking about my research work, which is a new distributed large graph coloring algorithm on giraffe. This work is part of my PhD that I have defended a few months ago. So, first of all, in this presentation, I will begin by an introduction to big graph. For big graph processing, there are several frameworks which are classified in various ways. In this presentation, I will briefly describe two categories. The first one is general purpose frameworks. The second one is vertex-centric frameworks. Then I will continue by giving an overview on graph coloring algorithms and the presentation of the new large graph coloring algorithm. To finish, I will give a conclusion and my future research work. Graphs are everywhere in our lives because they are an important data structure for describing relationships, interactions, and dependencies between objects. They are widely used for modeling complicated data in different application domains, such as social networks. Users are vertices connected by edges that represent some kind of interaction, such as friendship or following. Web graphs. Pages are vertices connected by edges that represent hyperlinks. Transportation networks, cities, towns are modeled with vertices, and the road that connects them are modeled with edges, and ways can represent the distance between two towns. Computer networks can be also represented using graphs. Graph can represent computers or devices as vertices connected by means of communication, and we can use the device hostname or an IP address to assign each vertex an unique ID. Currently, modern graphs are growing dramatically, and graphs with millions and billions of nodes and edges have become very common. Facebook is a dramatic example of a large-scale graph. Another example is the graph web of Google. Therefore, processing such graphs in the traditional centralized way is considered computationally hard and requires a huge amount of computational power to analyze. Thus, to deal with this situation, processing these graphs can be done by developing distributed algorithms under parallel and distributed platforms or large graph meaning frameworks. In recent years, and with the emergence of cloud computing, several parallel frameworks have been designed or can be used for large graphs processing. Each of these systems is designed to accelerate and to enhance the performance computation on large clusters. They are classified in various ways according to some criteria. If we consider the programming model, 4 categories may be distinguished: general purpose, vertex-centric, graph-centric, and edge-centric framework. In this work, we are interested only by general purpose and vertex-centric frameworks. Let's start with the first category. There are several general purpose frameworks that provide some good abstraction regarding large graphs processing, such as MapReduce and Spark, Apache Spark. The frameworks provide certain level of abstractions, such as coordinates and parallelism. MapReduce is a programming model that was designed to deal with parallel processing of large data sets. Hadoop is currently one of the most widely used parallel processing solutions. But does Hadoop work well for big graphs? In practice, graph algorithms can be written as sequences of chained MapReduce jobs that require passing the entire graph from one job to the next. Also, programmers need to design iterative jobs by manually chaining multiple MapReduce jobs and orchestrating their execution using a driver program. Thus, Hadoop is not appropriate for iterative graph computation. Let's continue with the second category. To deal with Hadoop limitations of graph processing, specialized large graph platforms have been designed. The majority of the graph specialized system adopts or link as a vertex philosophy and models a graph algorithm as a vertex-centric program in which computation centers around a single vertex. Vertex-centric computing frameworks are simple to program and widely applicable. Also, they are platforms that iteratively execute a user-defined program over vertices of a graph, and they have been proved useful for many graph algorithms. The first developed one was Pregel in 2010. The system has been designed for efficient, scalable, and fault-tolerant implementation on cluster of machines. As I said, the vertex-centric model adopts a think-like vertex philosophy where each vertex knows its local states, knows its neighbors, can send messages to vertices, can decide to halt its computation. But Pregel is not publicly available, and a number of graph processing systems that follow the same data flow paradigm have emerged, such as Giraffe. Giraffe introduced in 2012 as an open source project that clones the ideas and implementation of Pregel on top of Hadoop. Giraffe is based on the master-slave architecture. Workers are for performing processing, and the master is designed for coordinating and assigning partitions to workers. Computation proceeds by super steps. During each super step, each active vertex invokes the compute user-defined function in parallel. The function compute specifies the behavior at a single vertex and a single super step. There are some limitations in using vertex-centric system, such as stale messages, large communication synchronization costs. In this work, we have introduced a new graph coloring algorithm using Giraffe. Before describing this algorithm, let's have an overview on existing graph coloring algorithm. The graph coloring problem is one of the most well-known problems in graph theory. But what is the vertex coloring, graph coloring, and what is the chromatic number? A vertex graph coloring of a given graph consists of coloring all vertices by assigning a color to each vertex of the graph so that two adjacent vertices don't have the same color. The chromatic number is the smallest number of colors that must be used to color the vertices of the graph. Vertex graph coloring is one known problem in graph theory and has various applications in several domains, such as solving scaling problem and air traffic management. Graph coloring algorithms are generally divided into categories: exact algorithms and approximate algorithms. We can also divide them into three categories according to the computation system: sequential algorithms, traditional distributed algorithms, and systematic distributed algorithms. Based on Giraffe, we have introduced a new systematic distributed algorithm for coloring. The proposed algorithm runs in several supersteps. In each superstep, every active vertex executes the compute function of the algorithm. The compute function consists of three phases: the initial phase, coloring phase, and the conflict detection correction phase. In the initial phase, which is the superstep 0, each vertex V sends a message containing its own ID and its degree to all its neighbors. In the second phase, each vertex must have an initial color. The color of each vertex must be its order relative to its neighbors. The order is calculated based on the degree of the vertex V and the degree of its neighbors. In the last phase, which are supersteps 2 and the next superstep are designed to solve the resulting conflicts. After receiving messages from the previous superstep, each vertex checks if one or more of its neighbors has the same color. If it is the same, the vertex V recomputes its order within this set of vertices. After that, the vertex which has the greatest order changes its color. To illustrate this algorithm, let us run this algorithm on the graph of the figure 1. The algorithm requires 6 supersteps to color this graph. The progress of this algorithm on this graph is as follows. In the superstep 0, each vertex sends its degree and its ID to all its neighbors. In the superstep 1, each vertex computes its order within its neighbors using incoming messages of the superstep 0. Then it sets the obtained result as its appropriate color. Then each vertex sends its ID, its degree, and its color as message to all its neighbors. In the superstep 2, each vertex checks whether one or more of its neighbors have the same color. Vertices 1, 2, 3, and 6 detect that one or more of their neighbors have the same color. In this case, vertex 1 changes its color and chooses the smallest available color, which is the 0, blue. Then vertices 2 and 3 send to each other their IDs, their degrees, and their colors, and so do vertices 3 and 6. Vertices 2, 3, and 6 detect that one or more of their neighbors have the same color. In this case, vertex 2 changes its color and chooses the smallest available one, which is the color green. In the superstep 4, vertices 3 and 6 detect that they have the same color. Therefore, vertex 3 changes its color and chooses the smallest available one, which is the blue. Finally, only 2 vertices 3 and 6 are in active states and participate in the computation. In this step, vertices 3 and 6 don't have the same color, and they will not send any messages, and they vote to halt and stop the computation. The proposed algorithm is implemented in Giraffe and evaluated by using real-world graphs from the SNAP library. Our experiments were performed on the US Cloud Lab. We have used 10 compute nodes. So in order to show the performance of the proposed algorithm, this figure shows its comparison with the 4 existing graph coloring algorithm on GRaph in terms of the number of colors used for each data set. This figure shows the comparison of our algorithm with the 4 existing graph coloring algorithm on GRaph in terms of execution time. Finally, let's summarize. Okay. In this work, we have introduced a new parallel algorithm based on GRaph framework for coloring very large graph. The proposed algorithm has been designed for vertex-centric model. The proposed algorithm is efficient and able to run on huge graphs in a reasonable amount of time. To evaluate it, we have compared to existing GRaph graph coloring algorithms. The obtained experimented results have shown that the proposed algorithm outperforms the current GRaph algorithms in terms of the solution quality and the CPU run time. Okay. Thank you for your attention.
Thank you for your interesting presentation.
Sorry, I think I went over time. Sorry.
Well, I didn't measure the time, so thank you again for your presentation.
Thank you, and I'm happy to answer any question. Thank you.
Okay, thank you. So I'll give the floor to the audience if they have any question for this presentation. Any interest? So, what is the objective of coloring? Is it just for visualization or for processing?
No, it's not only for visualization. We can use coloring graph problem in several domains, such as scheduling problem or traffic assignment or
but
frequency assignments.
Why do you call it coloring? Why not just affecting some IDs or class IDs? That could be more general than coloring.
In graph theory, it is the graph coloring is the name of the problem. It is a well-known problem in graph theory.
For example, for visualization, well, if we have even distantiated vertices with different colors, but the colors are very similar, even if they are different, we cannot distinguish between the two for visualization.
For visualization of graph.
Yeah, but if we have, even if there are two distantiated vertices with different color, but which are very similar in chromatography.
It depends the
How
purpose
can we distinguish
of
this the one from the other.
It depends on the objective of the problem. I mean, the problem is that two adjacent is
two adjacent are different. Should be different. Yeah, should be different. But
should be different color.
Yeah, I know. But if we have a large number of classes, we will have problems to choose colors which could be distinguished by eye.
Yes, this is the objective. This is the objective of the algorithms of graph coloring.
But
to choose
to distinguish.
Yeah, it is NP-hard problem. It's an NP-hard problem. It's difficult to find the that all vertices, the adjacent vertices, don't have the same color, and in the same time you have to minimize the number of color used.
Yeah.
This is the main.
Okay, thank you. And for another question, it's for your example on changing the colors. Well, for the example you have done, I didn't know why do you change colors sequentially? Well, why not change the color of the node who has the more neighbors? For example, in your example, if you choose just to change the node 3, we will not change the node 2 and 6.
Yeah, this is this.
We will have to change just one node and not the others.
Yeah, in this example, because we have a small graph, we can't notice that the
just the way you do it.
the way, okay.
It's not optimal. What I have seen in your presentation.
Yeah, this is a small graph.
Sorry, you go sequentially from 1, 2, 3, 6. But if I have to choose, for example, change just 2, I will not change 1 and 3. I change just 6, or change change the node who have the more neighbors first, and after change the others.
Yes, I get you. This is a very small graph, and as you notice, these vertices are connected. And if we have another vertices, for example, they can change their color in the same time with these vertices, because these vertices, they are neighbor and they have common neighbors between them. So to don't choose the same color in the same time, they have to do that. But if we have another vertices, for example 9, for example, connected to the 8, and subgraph connected to the vertices 8, maybe I'm sure that they will change the color in the same time, in parallel manner. We can't see this in this example because they are this is a small graph, and they have common neighbors between them.
Okay, thank you. Thank you for the presentation, and I will switch to the next presentation.
Thank you, and have a nice day.
Have a nice day. We will switch to the next presentation if the presenter is us. Quality approach to analysis the causes failure in MOOC. Is there someone among us?
Yes, good morning.
Good morning. So okay. I'll give you the floor to present online.
Thank you.
If you have no problem.
Okay.
Could you share your screen?
Just a minute, please.
Committee and participants. First of all, I want to thank the Committee of International Conference on Cloud Computing and
could you you have a problem of audio?
Okay. To test my paper. Secondly,
it's a because we cannot see the video nor the audio is good.
Wait, please.
Good morning, dear committee and participants.
It's okay.
Could you share?
All, I want to thank.
Could you share your screen, please, first?
Okay.
You have a problem of screen sharing.
It's okay now?
Well, if there's a problem, could the technical organizer change to video presentation?
Wait, please. Now it's okay?
No sharing till now. For me, there's no sharing. No.
And now?
Okay. I think it's okay. Okay, thank you.
Good morning, the committee and participants. First of all, I want to thank the Committee of International Conference on Cloud Computing and Artificial Intelligence Technology and Application for acceptance my paper. Secondly, I will introduce myself. I'm Sukaina Sraidi, PhD student in University of Tofayl, Faculty of Science at Laboratory of Informatics System and Optimization. Today, I will present to you my work concerning quality approach to analyze the cause of fire in MOOC. Our plan include presentation of problem statement, methods and material, MOOC quality analysis model, proposed quality approach, conclusion, and perspective. The popularity of massive open online courses has gained recently a lot of interest in academia and industry. That they can provide a collaborative workspace, attract a large number of people due to accessibility of such courses to everyone in the world that has internet. However, the learning quality in quiet and convinced sense there is no suitable tools to evaluate this can be observed from the low completion rate of MOOC. Therefore, the analysis of data collected from the MOOC forums as well as their associated social media groups provide a helpful means to understand the behavior of the learners. Therefore, we aim to build a quality approach to analyze the cause of fire in MOOC. Many cases of problem can arise during the learning process, affecting the completion rate of the learners. In fact, these defaults are classified. Platform defaults. These defaults are related to the platform management. In other way, it reflects the student and platform interaction. Course quality default. In fact, MOOC course content is a significant predictor of the MOOC rotation. This can reflect the way the students that made their activity. Instructor support defaults. These defaults are related to the student-instructor exchange and generally positive sentiment expressed in relation to the course instructor had a large positive effect on likelihood of course completion. Methods and material. In our projects, we will use SVM machine learning algorithm. The goal of SVM is to find a distance margin in an n-dimensional space that classify two groups of data as shown, positive and negative learners. And the Ishikawa quality method is a quality tools that help us to identify the cause of a problem and understand the relationship between the problems and the root causes. MOOC quality analysis model. Our model is implemented on 5 steps. In the first step, the dataset can be obtained through application programming interface (API) or obtained automatically through web scraping. In our case, we will get data using API interface. After the text data acquisition, we proceed into second step on data pre-processing for subsequence analysis through to replacing all the emoticon with their sentiment and removal or hashtag and URL, stop word, no English word, punctuation, symbol, and number. After cleaning the data, we pass to the classification. We aim throughout this step detection of sentiment polarity in which we seek the polarity of a given text using the supervised machine learning algorithm, vector machine support. As a result of the classification phase, we can extract various features in order to determine the positive, negative, and neutral polarity, and to determine different topics. Afterward, we can build a dynamic dictionary to support the categorization stage. In fact, the dictionary will serve to categorize the positive polarity and negative polarity in 5 categories using Ishikawa method, motivation, moment, measure, and management in order to provide a clear structured presentation of the root cause and, by the way, to predict the risk of fire. Perspective. We aim to deal with the low completion rate as a crucial problem associated with the
There is a problem. Is the presenter disconnected from the session? Sorry for this problem. The presenter is disconnected. We will wait for some time to let him try to connect again. If not, in 5 minutes, we will close this session. I think it's difficult to continue. Sukaina, I think that Sukaina have a problem to reconnect. So thank you all for your effort, and see you again in the next version of the conference. Please don't miss the closing session that will be held at 12 o'clock local time, Morocco, GMT +1. Thank you.